Hello everyone. Let's see if the stream is going. Yeah, I can see myself. I can finally see myself. I think we are live. So thank you very much for joining us today. There are a few interesting recaps from the technical side of it that have been sorted out. So half of my screen is black, but I think I've figured that out, and I'm not sure exactly what happened to the LinkedIn stream either, but that's all right. Okay, cool. Let me share my screen and we start with the presentation for today. Okay, excellent. So today we're going to explore the instance calculator, but the real reason why we're here is to basically explore how to optimize the cluster and how to optimize instance sizes. That's what we're really interested in. So let's get started. So if you have any questions, you can write it down in the chat. Then we will get back to it at the end of the stream. And I've also got a special guest with us today, Ellie, which is going to join us later when we discuss costs, optimization, and sizing instances. Before we do so, just a little bit about myself. My name is Daniele. People call me Daniele, Daniele. All works. Chris called me D5E. That's I guess his favorite part. That's how much I'm into Kubernetes. And I spoke at KubeCon twice. I was lucky enough to speak at KubeCon twice, and I was one of the first 500 to obtain a CKA certification back in 2017. So yeah, a long way since then. Most of the time what I do is I teach Kubernetes. That's what I like to do. I like to teach and explain things. Hopefully I do it good enough, and you're going to see that today. But I work for a company called Learn Kubernetes, and that's my day-to-day job. But you're here today not because you want to see me, but because you want to learn something new on how to optimize your cluster and how to choose instance sizes. Let's get started. So before we actually talk about instances, we need to understand how Kubernetes works, right? So this is a quick recap. You're probably familiar already, but generally what we have is a collection of servers, and what we do is we install the Kubernetes control plane in one of these servers. We call it a control plane or master node, and then the rest of the fleet will join as worker nodes. Now, when we look at Kubernetes, we look at an individual cluster, and then we don't really care what's happening behind the scenes. We just deploy workloads as much as we want. And these workloads are basically just orchestrated by Kubernetes. So Kubernetes will find the right node and is going to place this container in the right instance size, in the right node. And this is great. And Kubernetes does this not just with servers of the same size, but you can have like several servers of different size with different features. What Kubernetes will do, it will just look at those resources and say, okay, I'm going to use the CPU and memory of this instance. I'm going to use the CPU and memory of the other instance, and so on and so forth. So the overall cluster memory and CPU will be the memory and CPU that is the sum of all the resources from all of the other servers that are joining as worker nodes. So how should you choose these worker nodes then? Should they be small or large? And how big they should be, and what kind of things you should put inside. So that's basically the question that we're going to try and answer today to a certain extent. And to understand where the complexity lies, I think it's good to take a step back and look at a fairly sort of very simple example. We're just going to touch on some areas that are relevant to us. So in this particular case, I've got a node instance, which is an 8 GB of memory and 2 CPU instance. And then my goal is to deploy a workload, so a pod, which has a single container which uses a request for 1.5 GB of memory and a quarter of a CPU. And then if you run the math, then I can basically fit 4 of those and still have space for memory available. So it should be fine, right? I should be able to fill this instance in full. So I try to deploy 3 replicas and it works. These 3 replicas are deployed on a node. But as I try to deploy the 4th one, it actually stays pending. And if I have a cluster autoscaler, then I notice that after a while, then a new node is provisioned and that pod is deployed in a new node. Which is somehow surprising. I was expecting that pod to be deployed in the first instance. So why is the cluster autoscaling creating a second instance? There is plenty of space. It turns out that things are a little bit more complex than that. We think that all the available memory and CPU in the instance is usable by pods, but the reality is slightly complex. We also have an operating system that uses CPU and memory, which is the Linux, most of the time is Linux, but sometimes you could have Windows containers as well, I imagine. Then on top of that, you've got the Kubernetes agent, so the kubelet, so also the kubelet is using memory and CPU. And then you've got something else called the eviction threshold, which is basically a mechanism to detect if the instance is running out of memory. So all of these 3 different blocks, they use memory and CPU. And those memory and CPU are things that you can't claim back. You can't use to run your workloads. It's as simple as that. But how are these resources reparted in the instance? So every cloud provider has a different sort of ideas on how much memory and CPU should be reserved to kubelet, operating system, and eviction threshold. Well, eviction threshold, maybe they all agree on a value, but most of the time they sort of have different opinions on how the memory and CPU for the kubelet is allocated. And in this graph, you can see that all of them sort of, and in this graph, I've got the memory at the bottom and the memory available to pods. So the total memory for the node instance at the bottom, so 1 gigabyte of memory instance, 2 gigabytes, so on and so forth. And then on the left, I have the memory which is available to pods. So what I basically done is I calculated how much memory is reserved to kubelet. I subtracted that from the memory of the total instance, and I'm left with the memory which is available to pods. And what you can see from this graph is that as my instance gets bigger, so 8, 16, 64, then the percentage of memory which is available to pods is also growing as well. So that means that it's more efficient to run workloads. So as I grow, as my instance grows, then the ratio between reserved resources and what's available to running workloads then increases. So these reservations, they are fixed. Well, they're not fixed. They have like a formula that you can calculate, and they sort of don't grow with the instance size, or they grow less than the instance size. So let's have a look at some examples. So this is an N1 standard 2 from GCP, and you can see that memory for the kubelet and operating system is sort of restricted to 23% of the total memory and CPU of 27% of the memory assigned to the total instance. So that basically means that 75% of the memory is available for pods to run. Similar to on D2, 3 on Azure. So if we just look at a similar instance size, we can see that the numbers are very similar, slightly higher on Azure, but you sort of get the idea. On Amazon Web Service, they have a very unique way to calculate these reservations. So you can see that here they are slightly lower, so just 19% for the kubelet and operating system, so and 78% of the memory is available to running pods. So what I think it's important to remember, each cloud provider has a different way to compute how much memory and CPU is available to pods. Now I'll show you the memory. Of course, the CPU follows a similar idea. as the instance gets bigger, then the reservation for the kubelets are basically negligible. That's what this graph is telling us. So, which brings me to the question: how should I size a node? Right? I know that the reservations are something that I need to account for, and I know that the reservations are very expensive. So the ratio between reservation and what I can actually use for running my pods changes as the instance gets bigger. So what I do is basically this. There are some limits on how many pods I can run on the node, and that's generally 110 or 250 pods per node. And generally what I do is I look at the memory from the instance, and then I subtract from that memory, I subtract the reservation for kubelet, operating system, and eviction threshold, and then that number I divide it by the number of pods that I can deploy on that node. And that basically gives me a grid of how small are these blocks. So I could potentially deploy 110 blocks, which are 257 megabytes of memory. Now, I probably don't have application that small, but that gives me like an idea on how granular, how these blocks are, the weight of these blocks, basically. And then what I do is I look in my application and say, this application is actually using 6 gigabytes of memory, and then I see how many units do I need for 6 gigabytes of memory. And that gives me like this size of this Lego block. And say, okay, I can actually try and fit this Lego block inside the instance and see how many of these Lego blocks, actually the Tetris blocks, I can fit inside. I can fit only 4. And then I repeat the same sort of exercise, but with a different instance. So in this case, I'm taking double the size of the instance and looking at 64 gigabytes of memory. And I try to basically segment this into units. And then what I do is I repeat the exercise. I look at the application. I see how many blocks I need to deploy my application. I can see that the blocks here are thinner because the unit is slightly larger. And I can see that I can fit more application into it. So you can see that this iterative approach, it gives me like I can try and see how many of these blocks can fit, and then I can change the instance and sort of see if there is something better that fits the current instance and how much wastage I've generated from that. Now, this is very simplistic, but it sort of gives me an idea of what it would happen if I were to deploy as many pods as I could in that instance, and what would be the utilization, and how many units I will waste if I were to do that. Now, it turns out that this sort of manual calculation can be automated, and that's basically the idea behind the instance calculator. So let me show you the instance calculator for an application which has got 6 gigabytes of memory and half a CPU. Okay, so this is the calculator which you can visit at learnk8.io/Kubernetes instance calculator. So I'm going to say 6 gigabytes and half a CPU. And then I'm going to order the instances where the cost of the pod is lower. And what the instance calculator, let's do like this. 6, half a CPU, and then order low to high. And I can see then from the bottom of, from this diagram at the bottom right of the screen, that if I select this as R6A 32x large, then I can fit 178 pods, and each pod is going to have 6 gigabytes of request and half a CPU. And how well I'm utilizing this particular instance? Well, I'm utilizing all the memory available, so very well, and I'm utilizing 70% of the CPU, which is allocated by the instance. That basically means that I could bump up the request, and I can see the efficiency and the overcommitment going up as well. So, if I were to optimize my my request and limit, sort of, to model what kind of application I could deploy in this instance, then this would be the max that I could fit. So this tool is also giving me an idea on how much it's going to cost me to run a single pod. In this case, 98 cents. I can also look at options like smaller, so similar size, but smaller instance sizes. It's just giving me sort of a similar idea how many pods I can run, how much they would cost if I were to run 135 pod in this instance, and so on and so forth. Cool. Let's go back to the slides. I think the other interesting thing that this calculator can do is you can see that we're basically selecting an instance size based on the request for the workload. So you have an application and you basically derive what would be the best instance which is going to run this application. That's basically the idea behind the calculator. But how do you actually define these blocks? How do you define these requests? And how does request useful to Kubernetes, right? What's the logic behind this calculator? Should I go with smaller request, higher request? How do I figure out the right requests for my application? Well, it turns out that requests, the way requests work in Kubernetes is basically they are used by the Kubernetes scheduler to decide where a particular pod should be deployed in the infrastructure. And so Kubernetes doesn't know how much memory and CPU your application will use, the actual users for an application before running it, right? And the scheduler basically needs to decide where this application is going to run. So it can't know in advance where the actual utilization. So what we do is we say to the scheduler, hey, this is the request. This is what we think is going to be the actual usage. So the memory request is going to be 6 GB. The CPU request is going to be half a CPU. Can you please find a node for this workload? And what happens is these are basically requests. So this is what we think is going to be like the actual, the average usage for this application. And we basically say we want at least these amount of requests for the application. But what happens is these requests could actually increase. And they usually increase towards what we call the limit, right? So they could go from, 512 megabytes of memory to 4 gigabytes, and it could go to a quarter of a CPU to a full CPU. And limits are great because they can limit how much memory and CPU you can use, but at the same time, they also provide some challenges, which is, okay, if all the pods are deployed, but they all use resources until the limit simultaneously, so they all grow the same size at the same time, what is going to happen, right? And this is basically where things get interesting because you won't be able to run as many pods, as simple as that, right? And two things could actually happen. One is your actual users will grow until the limit, or the opposite is your actual users is lower than the request. Now you might think maybe the second is better. I'm happier. I'm happy to have a higher limit, higher requests, and actually lower usage than the opposite. Well, it's not always that as straightforward, and I'm going to show you why. So let's have a look at a particular instance that can fit 6 pods, and these 6 pods have got like 6 slots, which are the requests. And then what can happen is if the actual usage is less than the request, then all the area that you see here in orange, then that area is underutilized. It means that it is allocated for the application, but the application is never utilizing it. So it's basically just wasted money. So let me show you how it works with the graph. So if you think that the application is, the request is 4 gigabytes, but the actual memory usage is below that, you're basically overpaying for your pods because those resources will never be used. Now the opposite is also interesting because what happens with the opposite, imagine that you define these requests and you have some limits, but the average actual usage is more than the request, right? What is going to happen in that case? Well, in that particular case, we're using more, in average, we're using more resources than what we define in the request. And the problem with that is that the application could actually, we won't be able to fit as many pods just because we are underestimating what was the right requests. I think it's best to visualize this with an example. So let's have a look at the calculator. I'm going to choose a 6 gigabyte of memory. So the same pod as before. I'm just going to set the limits twice as much as the request. Let's see what we get. So I've got my application for 6 gigabyte, half a CPU. I'm going to set the limits to 12, and 1. And yeah, let me just refresh and oh, I've got it. There we go. Missed that 0.5, 12. Oh, it's this one. Okay. And I'm going to order by low to high. Okay. So again, we go back to the R6A 32x large. And what is basically this widget is telling me is that if all the pods were to go and grow their usage until their limit, then I wouldn't need an extra instance to run all of the pods, because just there isn't enough space. And for the CPU, well, we basically need 40% more of an instance, so almost half of an instance to run all of these workloads. That's what it's telling me. So this is also reflected in this other widget called pod estimation widget. This pod estimation widget, what it does, it basically calculates the request and how much is going to cost this pod when the actual usage is equal to the request. But then we have like an interval that we can select where we basically say, what if the value, what if the actual usage for memory and CPU is 50% more than what we actually estimated? So what if these 9 gigabytes and 0.75 CPU cores? In this particular case, what happens is we are overpaying. So if it is less than 50%, the actual, we say that the actual usage is 3 gigabytes of memory, but we define 6, then we're basically overpaying 50% of the price. So we're wasting 49 cents for the instance that we are paying per pod. But on the other side, if 50%, what we're basically saying is if the request were to grow until 9 gigabytes, then the cost per pod is not 98 cents anymore. Actually, it is closer to 138, which is 50% more, or a little bit, yeah, closer to 50% more. And if I go and try to increase this, these numbers, you see, they don't grow exactly linearly. There could be a bump where it's going to be way more expensive than the requests. So what I'm trying to say here is that sometimes it is very difficult to estimate the size and estimate the error for your requests. And then estimating the error for a request, it will impact the cost of running your workloads. And to explain this in a little bit more detail, we've actually real example from a real application. I've got Ellie from Perfect Scale today. So Ellie, I'm just going to switch and let me just show Ellie. I'm going to hide myself. Hopefully it's going to work. Ellie, to you. What happens to real instances?
Hello, Daniel. Thank you for having me here. Hello, everyone. Thanks for joining us today. So in real life, we usually have more than one pod, and we usually have this problem of day 0, day 1, and day 2. Day 0 is when we plan everything, and this is where Daniel's the calculator is very helpful to give kind of rough estimations to the management what we are going to talk here about. But then there is a day 1 when you build everything, and there is day 2 when you start operating your cluster. And this day 2 is not one-time operation, but this is a continuous process where you running your clusters over time. And as you know, over time, you're going to change your application, you're going to change the architecture. This is going to affect the utilization of particular pods. And particular pods may need different amounts of requests and different amount of limits for the CPU and for the memory, and this will also affect your scheduling and your eventual stability and build all together. And this is why in Perfect Scale we developed the platform to address all those needs. And I will show you how those things are looking in large scale systems. So Daniel, I need permission to share a screen. Sorry, we have technical hiccup here. Yep, amazing. So here is an example of the environment, which is running 5 different clusters. We will focus on one of them. So in this cluster, we have 158 different workloads, deployments, stateful set, jobs, whatever we may have in our cluster. Recommendations of how much resources we need for each and every workload. We can categorize them. For example, we can easily detect the under-provisioned workloads, let's say the under-provisioned CPU requests, where we do not have enough reservation and we eventually may face starvations or this kind of problems. Let's look into this first workload here. This is some job. And this job is requesting 3 cores of CPU and 10 gig of memory. However, it normally uses somewhere between 3.5 to 4. So in order to not become a busy neighbor and try to allocate and try to compete with other workloads on the node, we would like to set more CPU and give better hint to the scheduler so our system will become more stable. On the other hand, we can look into the over-provisioned workloads. Let's focus on this Ingress Nginx controller. We spending here $17, out of which $15 is going directly to trash. No one ever uses those resources. And the reason for that is pretty simple. The current request is half core. We have somewhere between 3 to 6 replicas, but none of the replicas normally not using any more than 20 millicores of CPU. So this workload is requesting like 10 times more, 20 times more resources than would be needed in any given situation. And then we can review how the infrastructure behaves, or what is the eventual decisions that were made by the scheduler. What we can see, and this is a typical picture of typical cluster, we have some spot instances to run our to run our stateless applications. We have stateful applications running in different area. And if we focus on, and we see some slight cost increase, the cost increase in spot instances, so let's review it. The main cost increase was in last 2 weeks, mainly in this type of machine, M6-2A large, and we can select this machine, and then we can understand how the behavior was, what workloads were scheduled and running in these machines, and by that we can understand who exactly is the cause for scaling up, for increasing the cost, and how we can address those workloads and what exactly need to be done in order to improve them. So this is more of day 2 operations, when things are getting complex, when things are getting, when you have multiple chefs in the kitchen managing multiple workloads in your clusters, and you have a DevOps or platform engineering team who is eventually setting up the machines and deciding which machines to use. And again, this is crucial because let's say we have if we sort everything by the cost. So in this type of machine, 5A2X large, we're getting 8 cores, 31 gig of memory for 0.2 cents per hour. At the same time, we have another machine with half memory with the same cost. So basically, we kind of overpaying if we're running here. And those changes can be, and those gaps can be multiplies of 2, 5, 10, etc. So understanding where where your workloads are running and making your workloads right-sized is crucial to have efficient and stable operation over day 2.
Thank you very much, Eli. That was very helpful. Let me just share my screen again so we can. Oops. Let's have a look. Okay, I'm gonna pause you, Eli. I'm gonna enable it later. Okay. hopefully you can see my screen. So Ellie explained how this calculator works in real life. And with that, I mean, what if you were to actually measure these values instead of just estimating it with the calculator? And it showed us, what kind of other things you can do. And it's important to actually focus on this because the calculator is actually, it's very simple. It's just you can use a single workload. It works on a single node. It actually considers all the instances, and sometimes, considering instances with CPU burst is not always a good idea. And it also assumes that the actual user is equal to the request, which I think those are like good enough for estimation. But if you look at the reality, at least the reality that Ellie showed us is that, there are considerations that we need to be done. So for example, if you're using any scheduling constraints, then things are more complex, right? You won't be able to utilize all of the node instances at the, as efficiently. Or the other things which is quite common to misconfigure is the requests. So you have too high requests and too low requests. Of course, if you try to model those in the calculator will happily take all of the values, but in reality, you will end up overpaying or underpaying a particular pod. So what I'm saying is that it is good, the calculator is good to actually get an estimation. You can get an estimation very quickly. You can also go back and compare instances. So I can go back and choose what would be live if I were to go AWS or Azure, GCP or Azure. I could compare the value and see what option do I have if I want to migrate from a cloud to another. But at the same time, it doesn't actually measure runtime performance. So there might be some gaps that need to be filled with a tool that can measure that. So when it comes to the tool that can measure that, I think there are basically two big categories. One is what you can find in open source tooling, and I think here you can find a few examples. So Kube Resource Report and KRR from Robusta, and Condense, which is like a new project just came out, which was I found quite interesting. Those are just like tools that you could use to do either reporting or to just analyze how much request and memory and CPU you should set on your workload. And then on the other, we have like all of these products like PerfectScale that basically are designed to dig a little bit deeper into those values. Now, you might look at this slide and think, wow, there are so many of them. And I'm going to add on top of that, yes, there are so many, and so many new companies are creating products like this. But I think the reality is I'm grouping all of them together, but I think the reality is quite different. So what I found in the market, and at least, speaking to Ellie, what I found is that each of these products, they actually see they see the same metrics, but they actually interpret the metrics in a different way. They look at how memory requests and instances are assigned, but they sort of have their own thinking about how this should translate into actual costing or advice on how you should change your workloads. So you might find that some products are more like, okay, this is just a report, and then there is no action for you. You have to basically guess what the next step is. And you can find that some others are basically just doing costs because they have the data, so they can do some sort of reporting. And then there are other tools which are basically more actionable. They say, okay, if you were to change this is what it could happen. You could save money, right? So I think my advice would be, yes, there are plenty of tools that try to tackle this space, but not all of them have the same goals. So some are more focused on actually saving money and being efficient. Other are more like reporting, and others just like bolt on to an existing service. So my advice would be, sort of exploring what's the right angle for your cluster. Now, so that I'm going to wrap up what we discussed today. Hopefully you find the webinar useful. So what we've done today is we looked at node resource allocation, so how these instance sizes in Kubernetes are using memory and CPU, and we look at memory and CPU reserved for the operating system, and the kubelet and the eviction threshold, and how the CPU is reserved as well. We had a look at how limits and requests are used by workloads and Kubernetes. So we looked at how an application could actually define requests and then grow to the limits, and what happens when that happens, when all of the applications grow their memory usage and CPU usage towards their limits. And then we actually compare this with actual usage of resources. So I said that my application should use 6 GB of memory, but it's using 3 GB, or it's using 9 GB. What does it actually mean for me, and does it affect my cost? Yes, it does, and how much? So I think this is very important to actually help you give a better estimation. And so in that sense, we had a look at the calculator and then real tools that measure the actual performance based on the metrics collected in your cluster. And then the last part, we had a look at these costs. So how costs can be, a metric that can be just reported, or it can be an actionable advice that you can use to change the configuration of your cluster. Yeah, that was all for today. Thank you very much for joining. And thank you very much to Ellie. So yes, if you are into Kubernetes training, I'll list some link you down below in the description, so you can check them out. If you're interested in keeping up to date with Kubernetes, I publish a newsletter every week about what I find interesting, articles, events, jobs, anything. Again, you can find a link in the description if you want to subscribe. And it looks like this. And yeah, the other thing I want to say, thank you to PerfectScale. So PerfectScale supported the development of this tool. So this tool is free. You can go and play with it, and hopefully you can save a fair amount of money by doing so. And then the changes that we've done, they've been supported by PerfectScale. So thank you very much, PerfectScale. It's been an excellent partner. If you're interested in digging more into this topic of how do you actually choose the best instance type, I think PerfectScale is going to run a second webinar linked to this. We will find the link, again, the link in the description. They will sort of dig a little bit more, and they will compare the theory that we described today with the actual practice. So the demo that actually Ellie gave, then they're gonna go a little bit deeper into that and explain how things work in the real world. Yeah, that's all I wanted to show you with you today. If there is any questions, I'll be able to answer those. Let me just bring Ellie back. There we go, and stop sharing my screen. And then I will just try to figure out where the chat is, and if there is any questions from the audience. Cool. Let me know if there is any questions. I'm trying to figure out where my stream is. Okay. I don't see any other questions. Ellie, is there anything you would like to share before we close the stream?
Yeah, so one last, two last closing notes. We haven't spoke about this a lot, but in general, the resources are one of the aspects that you need to configure. But the second aspect, when you come into the things like real production, what you would like to consider is also your blast radius, and we definitely encourage you to configure affinity and taints and tolerations and different scheduling constraints to make sure that your pods are not arriving to the same node, and then when this node is accidentally goes down, your entire application goes down. You always need to have some kind of extra amount of resources, because it's very hard to keep the request and the limit in right kind of size. So with all this, PerfectScale definitely can help you, and you can start your trial today for free.
Okay, excellent. And let me ask you, I think, I'm really interested. This, I've been studying and building this calculator over the years. and you've seen quite a few clients and optimize their workloads. What is the biggest mistake? What do you find more often when it comes to, misconfiguring clusters?
Yeah. So in most of the cases, as I can see it, people, it's in many situations lack of knowledge, like understanding that request is the part that you are allocating, and the limit is where your safety valve is. And what Kubernetes guarantees you is just that it will try to allocate what you ask to allocate, and it will kill the pod when when you reach the limit, on one hand. The second big mistake is the differentiation between compressible and uncompressible resources. Your CPU is compressible, so if you a little bit of under provisioned it, the worst case scenario, what will happen is you will have a little bit of latency, and but your pod will still running. If you underestimate the memory, then the result will be unkill, and your pod will go down. And this in many situations can cause a kind of chain reaction where other pods, other replicas of your pod, trying to withstand the remaining kind of load and blown up too.
Okay. And let me ask you one last question. I think this is just out of curiosity, I guess. Is this issue primarily with one type of language or runtime? Do you see this more like on Java or .NET, or is it just across the board?
So from my personal experience, after seeing hundreds of different pretty common for any language. From what I see for Golang, it's less common. For Java, it's definitely way more common because Java is way more complex. And Daniel have an amazing blog on that also.
Thank you. Okay, that's interesting. I didn't know Go was actually better in that sense. So I think that's something worth exploring for me. Okay, Ellie,
One maybe last note, we haven't mentioned Carpenter, which completely revolutionized this entire space. So previously we had cluster autoscaler, and not many people know, but cluster autoscaler expects you to define machines that you want to scale up, but he also expects you that those machines will be the exact same size. So you can choose whatever machine you want, but all of them need to be 16 by 32 or something like that, as an example. Carpenter completely changed this paradigm, and I really encourage you to migrate to Carpenter as fast as possible. This is open source, this is battle proven, and it's amazing.
Yeah, I think that we will see a lot of new technology on that. I see a question, someone asking, is eviction threshold different for each cloud provider? The answer is it used to be. It used to be until Azure released AKS 129. Before 129, the eviction threshold for Azure was 750 megabytes. And then after 129, it was tuned down to 100 megabytes. And now it is 100 megabytes for all major cloud providers. Yeah, that's the answer to the question. And yeah, I think Carpenter, since it's been donated to CNCF, we will see a lot of innovation in the space. I'm really looking forward to this. Yeah, exciting stuff. Cool. Excellent. Ellie, thank you very much for coming and joining me today. I appreciated your insights. As usual, it's very nice to have someone on the field actually, doing this stuff and bringing a new perspective to these sort of topics. So thank you very much for that. Hopefully see you in another stream. And for the rest of you who are listening, if you'd like to stream, you could click on subscribe and get ready for the next one. I'm looking forward to next month as well. And thank you very much for joining today.
Thank you.
Thank you.
Bye.
Bye.